Section: Introduction. In this section, we discuss the advancements in language model-based agents, which are becoming increasingly capable of handling digital tasks like web navigation and mobile app operation. Currently, these agents rely on a fixed set of examples for training or in-context learning. While this approach allows them to perform well on similar tasks, it limits their ability to adapt to new contexts or environments. They struggle to identify and learn reusable workflows that could help them tackle more complex tasks. Additionally, since they address each task independently, they miss out on learning from previous experiences, which hinders their ability to improve over time. Inspired by how humans learn from past experiences to guide future actions, we introduce the concept of Agent Workflow Memory, AWM. AWM helps agents develop workflows by extracting reusable routines from their actions and storing these workflows in memory to assist with future tasks. Each workflow represents a goal and captures essential skills needed for solving complex tasks. For instance, AWM can learn to find a place by its name from initial examples and build upon this to create more complex workflows, like get the zip code of a place. This ongoing learning process allows agents to continuously enhance their capabilities, leading to significant performance improvements compared to traditional agents. AWM can function in both offline and online scenarios. In offline mode, it can utilize high-quality annotated examples to extract workflows and aid in task execution. In online mode, it can operate without supervision, generating workflows from its own past predictions that are validated by an evaluator. We evaluate AWM on two benchmarks: Web Arena, which focuses on execution-based evaluation, and Mind2Web, which covers a broader range of tasks. AWM shows remarkable improvements, outperforming existing methods and demonstrating its adaptability across different tasks and domains. In the following sections, we will outline the web navigation task, describe how we represent workflows, and explain the AWM mechanism and its various implementations. We define our problem statement, considering agents with a language model and a text-based memory that includes built-in actions. To address a task defined by a natural language instruction, the agent interacts with an environment, observing states and executing actions in a loop until the task is completed. Our goal is to derive useful workflows from past experiences, which we will incorporate into the agent's memory to guide future task-solving efforts. Section Summary. In this section, we propose Agent Workflow Memory, AWM, to enhance language model-based agents by enabling them to extract and learn reusable task workflows from past experiences, thereby improving their adaptability and performance in complex tasks. AWM allows agents to continuously build on their knowledge, leading to significant performance gains across various benchmarks, even in scenarios with limited or no annotated examples. Section: Workflow Representation. In this section, we describe our workflow representation, which consists of two main parts: a textual description of the workflow and a sequence of steps needed to complete it. The workflow description outlines the high-level goal of the actions involved, and we create this by summarizing the workflow's purpose using natural language tasks. The workflow trajectory includes a series of steps that correspond to the actions described in the workflow. Each step has three components: a description of the current state of the environment, the reasoning behind the agent's decision on what action to take, and the action itself, which is an executable command in the environment. At the heart of our approach is an induction module that generates a set of workflows from past agent experiences. Each experience includes a natural language task instruction and a sequence of actions taken to address that task. The induction module processes these experiences to produce workflows. To enhance the accuracy of the workflows, we use a language model that helps us identify common subtasks across different experiences. Instead of focusing on specific tasks, we encourage the model to extract more general subtasks that frequently appear in various instructions. We also abstract specific examples to improve the generality of the workflows. Once we have induced the workflows, we integrate them into the agent's memory, augmenting it with this new information. When the agent receives a task instruction, it can now generate a series of actions using this enriched memory. In offline scenarios, we can utilize additional annotated experiences to induce workflows separately from the inference process. We first create workflows from training examples and then incorporate them into the agent's memory for solving test instructions. In online scenarios, where we may not have extra experiences, the agent processes test queries in real time. It generates action trajectories for each test task and evaluates their success. If successful, these trajectories are transformed into workflows and added to the agent's memory, allowing for continuous learning and improvement as it processes more tasks. We then assess the overall success rate of the predicted actions across all tests. Section Summary. In this section, we describe a workflow as consisting of a textual goal and a series of actionable steps, emphasizing the importance of high-level task descriptions for effective learning. We introduce an induction module that generates workflows from past experiences, enabling agents to utilize these workflows in both offline and online scenarios to enhance their problem-solving capabilities. Section: Experiments. In this section, we conduct experiments on two key web navigation benchmarks, Web Arena and Mind2Web. For each benchmark, we first describe it and the top-performing baseline methods, then introduce our AWM approach, highlighting its superior task success and generalization across different setups. We apply AWM on a website basis, grouping examples by their associated websites and running AWM on each group. This approach keeps a small set of relevant workflows for the test tasks. For Web Arena, we have 812 web navigation tasks across 5 websites, covering 4 main application areas: e-commerce, social forums, collaborative software development, and content management. Web Arena allows for thorough evaluation of the correctness of agent actions. We use the state-of-the-art method, BrowserGem, which modifies the agent's default action space without relying on human annotated site-specific knowledge. We also run a version of BrowserGem that only uses accessibility tree representations for web pages, ensuring a fair comparison. Additionally, we compare our method to STEP, which relies on 14 human-written workflows specifically designed for Web Arena. Unlike STEP, our method does not use human supervision and is not tailored to this benchmark. We utilize GPT-4 with a temperature setting of 0 for stable outputs. Since Web Arena only provides test examples without high-quality, domain-aligned examples, we perform AWM in an online setting. Our main results show that AWM achieves the best published results on Web Arena, outperforming the BrowserGem baseline by 12 absolute points and a 51.1% relative increase in overall success rate. AWM also surpasses STEP, which uses strong human supervision, by a 7.6% relative increase in success rate. Across 5 websites, AWM significantly improves agent performance over the BrowserGem baseline, with absolute point increases ranging from 11.8 to 30.7, demonstrating its broad applicability. We also assess the average number of steps taken to complete tasks, finding that AWM requires about 2 fewer steps per example than BrowserGem. Compared to the AutoEval method, which needs extra evaluation steps, AWM uses 40.8 fewer steps on average, indicating that AWM achieves high success rates while maintaining efficient task execution. To illustrate the efficiency of our AWM method, we show the cumulative success rate during online evaluation, tracking the average success rate of the first K completed examples. The agent shows a rapid learning curve initially, acquiring essential workflows and achieving higher success rates. As learning progresses, agents develop more advanced workflows, with success rates stabilizing at a high level early on. This highlights AWM's effective learning process, which significantly enhances performance with just a few examples. We also explore cross-template workflow generalization. Some tasks in Web Arena share similar trajectories due to the way the benchmark is constructed. AWM improves the success rate within templates, meaning that learning from one successful example makes it easier to solve other examples from the same template. To test if AWM can generalize across different templates, we select a subset of Web Arena examples from non-overlapping templates and run AWM on this group. Our results show that AWM still achieves the highest performance overall and for each website split, demonstrating that AWM can effectively generalize workflows across different tasks. Section Summary. In this section, we experiment with our AWM approach on two web navigation benchmarks, Web Arena and Mind2Web, demonstrating its superior task success and generalization capabilities. Our results show that AWM outperforms existing methods, achieving higher success rates and more efficient task completion across various domains, while also exhibiting effective learning from limited data and cross-template generalization. Section: Building increasingly complex workflows. In this section, we demonstrate how AWM can create increasingly complex workflows. To illustrate this, we conduct a case study that reveals the workflow mechanism. Initially, the agent learns to find a place by its name, by summarizing past examples. Later, when it needs to find the zip code of a location, the agent uses the initial steps from the existing workflow and adds new steps to complete the task, resulting in a more complex workflow called Get the Zip Code of a Place. Next, we discuss Mind2Web, which involves web navigation across various tasks and domains, highlighting the versatility of agents. Each task has a set number of steps, and at each step, the agent predicts an action. We evaluate this prediction based on three metrics: element accuracy, correct page element selection, action F1 score, correct action on the element, and step success rate. Both element and action must be correct. After completing all steps, we measure the task level success rate to see if the entire task was executed successfully. We explore both offline and online settings for workflow induction, comparing AWM with two leading methods, MindAct and Synapse. MindAct uses web page element filtering and a multiple choice format, while Synapse employs a trajectory style and enhances relevant examples. We incorporate element filtering from both methods and replace retrieved examples in Synapse with reusable workflows to highlight their advantages. We ensure a fair comparison by using the same models for both workflow induction and action generation. Our main results show that AWM, when run offline with both GPT models, consistently achieves the highest success rates at both step and task levels, outperforming the baselines by notable margins. The improvements primarily stem from better element selection accuracy. We also compare AWM to Synapse, noting that AWM achieves higher element accuracy and step success rates. While Synapse relies on concrete examples, AWM's abstract representation reduces bias in element selection, leading to better performance. Additionally, AWM's reusable subroutines can be applied flexibly across different tasks, unlike the full example trajectories used by Synapse. Finally, we observe that despite AWM's accurate element selection, it has slightly lower action F1 scores than MindAct. This may be due to the workflows guiding the agent towards specific actions that may not always fit the current context. While following workflows generally leads to successful outcomes, agents still face challenges in knowing when to deviate from these guidelines. Section Summary. In this section, we demonstrate how the AWM agent builds increasingly complex workflows by learning from past examples, allowing it to adapt and extend its capabilities, such as transitioning from finding a location to obtaining its zip code. Our results show that AWM outperforms baseline methods in success rates due to its abstract, reusable workflows, which enhance element selection accuracy while also highlighting challenges in diverging from established workflow guidelines. Section: Online AWM enables generalization. In this section, we explore the AWM in an online context, similar to the Web Arena experiment setup, where we do not need extra training examples beyond the test queries. This approach allows us to easily generalize across different websites and domains, which we investigate using the Mind2Web datasets cross-website and cross-domain tests. Alongside the MindAct baseline, we also evaluate our AWM setup by randomly choosing workflows from the training set to enhance memory. For cross-website examples, we select workflows from the same domain, while for cross-domain, we choose workflows from various domains. We perform AWM by iteratively creating, integrating, and using workflows based on test inferences. Our results show that both AWM setups significantly outperform the MindAct baseline, achieving improvements in step success rates across different scenarios. In the in-domain, cross-task scenario, AWM methods perform similarly. However, we notice that AWM can sometimes create workflows from incorrect model predictions, which can hurt performance. In contrast, AWM effectively addresses the differences between training and test examples by focusing solely on test queries, leading to better targeted workflows and higher success rates. If high-quality training examples are available, AWM could further reduce the gap issue. When we apply AWM to unseen websites or domains, it shows better generalization compared to other methods. The performance gap increases as the differences between training and testing data grow, whether between different websites or domains. Since AWM does not depend on training data, it remains unaffected by these gaps. Nonetheless, AWM still benefits from similar workflows from previous experiences, as shown by its significant improvements over the MindAct baseline. We also experiment with different ways to represent workflows, including subroutine and abstract formats, descriptive texts, and enhanced observations using website HTML. We compare our abstract, subroutine-based method using language models to a rule-based method that lacks context. The rule-based method extracts action sequences and removes non-executable steps to create workflows. Our findings indicate that both methods perform similarly, with a slight edge for the language model approach, which is more efficient and results in fewer steps. Our analysis reveals that workflows generated by the language model are more detailed, helping agents avoid unnecessary steps and making the task-solving process more efficient. Section Summary. In this section, we explore the online application of AWM, demonstrating its ability to generalize across websites and domains without additional training examples, leading to significant improvements in success rates compared to the MindAct baseline. We also investigate optimal workflow representations, finding that our LM-based induction method is slightly more efficient than a rule-based approach, producing finer-grained workflows that enhance task-solving efficiency. Section: Mind2 Web Results. In this section, we present our findings on the Mind2 Web results. We observe that AWM with language model integration, referred to as AWM-LM, shows an improvement of 2.8 points compared to AWM. While using full examples can lead agents to favor similar elements, AWM with iterative language model integration, or AWM-IT-LM, reduces this bias by providing a more abstract representation of specific contexts in workflows. Additionally, AWM-IT-LM utilizes commonly used subroutines, making them more adaptable across different test examples, unlike the full example paths from AWM-IT-RULE, which are less frequently repeated. Overall, our results suggest that the abstract and reusable nature of workflows enhances the effectiveness of the AWM-IT-LM method. Next, we explore workflows in descriptive texts. AWM formats workflow steps as code, and we compare this with a textual format to determine which is better for agent memory. We prompt the GPT 3.5 Turbo model to express the action trajectory from previous experiments in natural language. For instance, the action click, suit id, is verbalized as click the suit button. We maintain consistency by using the same observations and thoughts from code actions in the text actions. From our results, we find that AWM achieves slightly better accuracy in element selection and step success rates, improving by 0.6 and 0.3 points, respectively, but it shows a decline of 1.2 in task success rate. Overall, we do not see significant performance differences between workflows in text and code formats, indicating that both can effectively enhance agent memory. Lastly, we discuss environment abstraction in workflows. AWM uses natural language to describe intermediate web page states, but showing actual states can help ground agents better. Since full HTML can be lengthy, we filter it using a relevance predictor and enhance each workflow step with this concise HTML that highlights relevant elements. We test GPT 3.5 Turbo with descriptions, HTML, and a combination of both. Our findings reveal that natural language descriptions are more beneficial than HTML alone, as replacing natural language with HTML results in a slight drop of 0.8 in step success rate. Interestingly, using both natural language and filtered HTML yields poorer results. We believe this is due to two main reasons. The combination significantly increases context length, making it harder for models to process correctly, and the filtered HTML often contains irrelevant items, missing correct elements 47% of the time, which can contradict natural language descriptions and hinder agent performance.